and speakers. Click Audio Setup to select your computer speakers or headset device. You can also join audio through your telephone. Select Use Telephone option. Dial the number listed and enter both the access code and audio pin when prompted. During the presentation, you have the ability to send questions to our webinar staff through the Questions pane. Simply type in your question and click Send. At the end of the presentation, we will do a question and answer session to answer as many questions as we have time for. There is also the option of asking questions directly to the presenter. To do this, raise your hand and we will unmute your microphone. This option is located on the Grab tab. If you prefer to keep your control panel open during the presentation, click View in the top menu and uncheck Auto Hide the control panel. We are now all ready, so we'd like to pass on to Ray Pavry, Managing Director of Sustainergy.
Thanks, Jesse. I'd like to welcome everyone to the Find All Electrical Jobs webinar series and have a pleasure in introducing Jeff Rogers, our speaker for today. I've known Jeff for a fair while through the IICA, where Jeff's done some very interesting presentations. As far as his background is concerned, Jeff's an engineering graduate with around 30 years experience in the application of control and safety systems in process industries. Jeff is a certified TUV, functional safety engineer, and has a long association with the IICA. He's been an author of various technical papers on control system and functional safety topics. Jeff's managed engineering teams designing and implementing process controls, information around turbo machinery and burner systems within oil and gas and power industries. Currently specialized in the application engineering and support of project teams, implementing functional safety consulting. Jeff has been working specifically on logic solvers and looking at it from that perspective. I'd like to introduce to you all Jeff Rogers.
Somebody else there for a minute. Just to bring up my screen on the screen there, so hopefully you'll be able to see that. I'll just wait a few seconds for people to see the screen come up. I'd like to thank you again for the invitation to do this webinar. It was, I like the format and I hope it's convenient for you to get some information, and I hope we have time for some questions at the end. Much appreciate that. Or I've got my email contact there and my phone number. You can always give me a call at any time. I'm happy to discuss this topic in particular at any time. What I'd like to do is just go through a kind of like an agenda. And we've got just less than an hour. I'd like to leave some time for questions. So I'll keep an eye on the time, and I may elect to zoom ahead if we're getting a bit behind time. But we'll get underway now. It is a bit of a commercial break here. I think I'm allowed one. This is just a description of the Invensys capabilities and areas of activities in safety and critical controls. Okay, so the talk will cover a bit about the history of the development of programmable electronic systems, which is another word for logic solvers in a safety and critical control context. It will talk a bit about issues when you're either choosing one to buy for the first time or maintaining one your organisation you're involved with owns, and I'll talk about some examples. So first of all, just to define what we mean by safety and critical control. Well, virtually everything is safety or critical to somebody. I mean, the air conditioning control on the wall in your office is, if it's working okay, it's fine. If it's not working okay, it becomes critical. We had a time in my office in Melbourne last week when or 2 weeks ago, went off for a while and it was out of control. So everybody was really impacted, and that's just a small smattering of the impact of a control system that might be operating a power station or a chemical reactor in an oil refinery. The impact of a malfunction there can be very, very large indeed, not just discomfort of people, but big economic impact or even a safety impact to people and the environment. So very much you would like to have some guidelines as to decide what is safety and critical, and unfortunately the answer to that is it all depends. And people hate me to say that, but it's true. So for example, this air conditioning system, if that happened very frequently, it's a small consequence, a little bit of sweat, if that happened every day, the company would lose so much productivity that we'd have to either relocate or we'd have to suffer some severe economic inconvenience, even after a relatively small, low consequence event at the time. If it happens a lot, it becomes a big consequence. On the other hand, you can have a hypothetical event like an aircraft hitting your building. That is almost too horrible to contemplate. It's going to kill a lot of people, passengers and also the people in the building, and probably people around the building as well. But it's, for most purposes, a very negligible issue. It's not going to happen very often, so you particularly can disregard it from a safety point of view. So even though that one has high consequence on this little graph here, it has such a low frequency that it's no great issue. So in the down-to-earth situation, if you have a business or a production line that's entirely dependent on the equipment under control, which is the plant that's being controlled by both the combination of the control system and the safety instrumented system, then if that represents a large part of the business, such as an oil refinery, the cat cracker unit is major, then you'd clearly call that critical. If you had a multi-train LNG plant where you had 3 or 4 or 5 trains producing LNG, sure, if one goes offline, you're not out of business, but just that one train might be making 3 or 5 million tonnes a year of LNG for export. Just that one train by itself is so large it becomes economically significant if you lose it. Same for a large power station. You might have 4 units, but if each one is 500 megawatts or 600 megawatts, then even one unit coming offline is have a big impact. So that's the kind of area that I spend most of my time playing in, and that's where a lot of the control applications in that sphere are both safety important and critical to the business important. So typically, that's to summarise that's where the process is either continuous or almost continuous, and a continuous process obviously has a start, and occasionally it will stop due to a trip or run out of feedstock or whatever it is. So even the best designed continuous plants have to cope with a startup phase and a shutdown phase. So there's really no such thing in actual definition as a truly continuous, but when we say continuous, we mean something that runs in the same state from day to day, week to week, month to month, and the shutdown. So hopefully no more often than 4 or even 8 years apart. Typically we're talking about plants that are handling hazardous materials. Obviously natural gas is explosive. A lot of materials are both flammable and also toxic, such as you might find in the chemical industry. They may be even toxic but not flammable, and even that presents a big enough risk to warrant a safety instrumented system. And of course then you'll have other applications of critical control. It might be in a high-rise building of a particular type, say as a hospital, that you can't evacuate very easily, or even a tunnel where you have a lot of traffic, a lot of cars and occupants of the cars in a tunnel, that by itself becomes a critical control environment. The most typical type of plant, this one came from a photograph that was shared by a gentleman from Orica. This is an ammonia plant in Newcastle. And it's a typical classic petrochemical process. I don't know how this is going to go on the screen, but you can, if I move my cursor there, you can see the two parts of the plant. There's an ammonia plant, and over the back here they make the ammonia into ammonium nitrate, which is used heavily in the mining industry as an explosive for breaking up the coal or other ore bodies into something they can shovel into a truck or put on a conveyor belt. So some of you might have seen this slide before. We're talking about, the distribution of failures. This little pie chart here is talking about the distribution of failures of a safety instrument system across its life cycle. And if you apologise, the colour may not come out too well on everybody's screen, but if you look at the legend there, you see that between specification and planning and implementation, more than half of the failures occur in the design phase. So that's why this is a really important topic for designers, and then a good part of the failures occur during the rest of the life cycle. Another type of process that's critical is a metallurgical process where this particular client from Queensland is reducing nickel ore with a high temperature furnace that moves the ore on a conveyor belt through this multi-zone furnace, and as you can see, the first zone it gets heated up by a lot of burners, and then it's maintained at a high temperature, something like 800 or 900 degrees. At that temperature, the side of these tubes is cherry red, and with a hydrogen atmosphere which they maintain in there to reduce the nickel ore, you can just imagine the potential for something to go wrong. But by itself, hydrogen, with the absence of any oxygen, won't be a problem. But if you have an uncontrolled situation and you lose control of your draft, you might get a mixture of air and hydrogen in there. With that heat source, even without it, at that temperature, you can get an explosion very easily. So that's a good example of a critical application. Or a more simple one from actually the same plant, but a much simpler application is just a single burner management system. And you might say, well, single burner management system, how simple can it get? The answer is that it can get relatively complicated in an industrial complex, as distinct from a simple single burner boiler in the basement of a hospital, because in the industrial complex, we've got upstream and downstream processing units to be concerned about, and also we've got I've just lost my train of thought there. Also, we've got, I guess, just the proximity of other people, and I guess just the sheer impact on the business if it malfunctions. So, a few ideas to be considered. Definition of a safety instrument system. Some of these are talking points just thrown out there from other contexts where I've used this presentation. A good question, it's often debated, is a burner management system a SIS? I think 10 years ago that would have been a bit of a debate, but I think these days most people accept that a BMS is a special case of a SIS. And this is a good one. If your plan hasn't had a safety impact, does it make it safe? I haven't, touch wood, ever had a accident in a car, but it doesn't mean I'm a good driver. I could just be very lucky. So it's not a good idea for me to drive around without a seatbelt on, so I do that even though I haven't had an accident. So you're looking to deal with some commonly held misconceptions, I suppose, that people will get from working in a hazardous plant for a long time. They can become, what we call it, insensitive to the risks they're actually taking. So that's unfair for new people coming into the plant who don't know aware of the risks or not prepared to take those risks that the older people might be. So it's good to be able to dispel some of those things, and that's almost a topic for a different day. Okay, human intervention. It's often the case you'll walk into a control room and you'll see an emergency stop button, and that's there for a very good reason. As the operator would like to have some way of bringing the plant to a safe state if all else fails. The issue for safety is that it's not a very reliable way. So if you only depend on emergency stop buttons to bring plants to a safe state, we'd have disasters all the time, because human beings are not very dependable, and in a crisis situation they become even less dependable. So most of the time plants are protected by automatic safety instrumented systems, but you will still have the big red push button just to satisfy that human and very real concern that what if this control system and the safety instrument system loses control, how will I then override it? Evaluation of SIS, I haven't got time to go into some of these things today. We'll look a bit at field devices and the voting systems that are involved in SIS logic solvers, but also in real world safety instrument systems. We'll talk a fair bit about the voting systems, different types of voting, consider which is safer and which have lower nuisance trip rates, and we'll maybe talk about where does failure rate data come from. Best data can come from your own plant, but of course any one plant usually hasn't got hundreds of years of operating experience with a logic solver. It might have cumulative hundreds of individual device years of experience with things like pressure transmitters or solenoid valves. So in 10 years you've got 100 transmitters, that's 100 times 10, 1,000 transmitter years of operation. It gives you some good idea. It doesn't tell you about long-term issues such as deterioration of seals and other material decompositions. So the best failure rate data will tend to come from generic data which is published and shared by organisations like AREDA. And again, I can point you to that if you like in the future. We talked a bit before about human reliability. It's actually quite low. Think about next time you're on an aeroplane. Presumably a lot of you travel for work, and if you travel by any of the airlines, you'll be travelling in an aircraft with 2 pilots. They're both highly trained, and they're cross-checking each other. So they're in that situation with all the training and all the other aids that aircraft have. It becomes an acceptable level of risk, actually safer than driving. If you're flying to Queensland, it's safer than driving to Queensland. But that you can't really extrapolate from that to having a plant where you've got a 12-hour shift operator operating by himself, or at least responsible for a bit of a plant by himself. His reliability is nowhere near as good as 2 pilots who've been rested and one's cross-checking the other and regularly retrained. Acceptable level of risk. By and large, the design criteria that people are applying to process plants, it actually makes them safer than the road, and that's just the fact. Safer at the plant than it is on the road getting to work. That's, like I said, that's just the way it's panned out. It's a good thing, I believe. It should be, especially when you think that on a road you have some ability to impact your safety, whereas if you're the driver, that is. If you're in a plant, you might be the victim of somebody else's mistake. So it's appropriate, I think, that we achieve a lower overall fatality rate in plants than we do on the road. 99.9% sounds like a good number, but if you actually work it out, if there's something like 4,000 commercial aircraft movements in Australia every day, 0.1% failures on those movements would be 4 crashes a day. So that clearly doesn't happen. So 99.9% might sound good superficially, but it's actually not that good when it comes to safety. So are there standards or guidelines? Yes, there are. there's international standards on this. IEC 61508 is used by logic solvers, by logic solver manufacturers, and devices that are used in safety instrument systems, and there's IEC 61511, and both of those are also Australian standards, and they're quite useful for the overall design of a safety instrument system. And finally, major hazardous facilities legislation. It's been adopted across Australia now. So all these major hazardous plants, gas plants, large ones, chemical storages, is granted by the respective state government if they've set up effective risk mitigations. So back onto the guidelines that you might look towards. You'll find if you look in any of the standards, you'll see a safety life cycle model, because you can, as we said earlier, that slide where you had the pie chart, more than 50% of your failures occur in the design phase. So that's people who didn't, on this left-hand side here, didn't design for the right faults or didn't design adequately for the plant hazards that existed. So it's very important to have a thorough and well-documented risk assessment process, and then once you have the risks identified, then have a well-documented process here for designing a safety instrument system. Now, the SIS logic solver is responsible for just a part of the plant safety. There are other contributors to the safety, and that's often indicated in this format of diagram, where you have some, down the bottom you have fundamentally some safety in view of the design of the plant. So you might make the piping and the pressure vessels able to withstand the highest pressure that could possibly be put onto that pipe or the pressure vessel, but that becomes uneconomical. So you'll have additional layers that you'll probably reduce the pressure at some point in the input to a plant to bring it back to an economical level. I haven't got time to go into the trade-offs there of economy versus risk, but by and large you accept the fact that there's going to be a process control system, which might be saying operating a pressure regulating valve. It can keep the process plant exposed, protected from the high pressure if it's working. If it doesn't work, you might have an alarm that says, hey, look, we've got a deviation from our pressure control loop. And backing that up is a safety instrument system. And if all of that fails, we have a release of gas or flammable material, then we might have a fire and gas system to, it's no longer a prevention system, it's now a mitigation system, but we might have a mitigation system which will hopefully detect gas and hopefully then do something about it, raise alarms certainly, and maybe depressurize parts of the plant. So this is often depicted in this format here, where we have risk across the right here, and we have an inherent process risk. We might be handling flammable gas, like we said. Some of the risk reduction is achieved by virtue of the basic process control system. Some other parts of the risk are absorbed or reduced by the relief valves, safety relief valves, and then whatever's left over is allocated to the SIS. And in the design situation, you'll be playing around with how much risk reduction you take here, say, in the safety valves compared to here. One of the most expensive things to do is make the piping and vessels so strong that they can withstand all the pressures that are ever going to be put on them, or ever could be put on them. That would be a rare situation indeed to see that. I want to talk about the logic solver today. So the logic solver can be pneumatic, can be relay-based, can be a solid-state logic system. More often than not these days, it's going to be, if it's a plant being built from scratch is going to be a programmable system, just because it's more flexible and it's easier to make changes, all those good things. And the logic solver might be in a single, dual, triple, quad or more channel configuration. So now we'll look at how to increase reliability. We can increase reliability by doing voting in our logic solver. We'll talk at length about that, and also give you some examples of where we do voting in the field devices that are also part of the safety instrument system. So at its primary level, voting of a 1 out of 2 nature, assuming that everything's de-energized at trip, which is the default setting for safety instrument systems and burner management systems, is 1 out of 2 voting is a minimum. If either of these inputs or either half of this logic solver decides to, it can de-energize this output by opening these contacts. That'd be called a 1 out of 2 vote. So even if this one here is stuck, this logic solver's got a problem, it's always giving me a 1 output, telling me to keep the output energized. The other half, or other parts, can outvote it, if you like, or override it, which is 1 out of 2 votes. So either of them can shut it down. There's another type of voting called 2 out of 2 voting, and you've got to be aware that there's a big difference between 1 out of 2 and 2 out of 2. A DCS, or Basic Process Control System, should vote this way, 2 out of 2, if it's redundant. Should have its outputs in parallel. So if this output here at the bottom goes open circuit, we can still keep our plant running by holding this contact in parallel with it closed. So that increases our reliability, because if we had voted that 1 out of 2 every time we had a fault in the DCS, we'll have a trip. So the DCS should vote 2 out of 2, and the safety system, if it's going to be 2 out of 2, won't be very safe. And I'll look at that in a minute. You can also do 2 out of 3, or in fact you can do M out of N. You can be 3 out of 5, 5 out of 9. An important thing about those multi-channel voting strategies is that, or multi-channel, i.e. more than 2, is you can have a fault and you can override it, whereas the 1 out of 2 vote, the classic 1 out of 2 vote, a fault, if it's in a safety-related nature, will cause it to shut down. But in a multi-channel system with more than 2, i.e. 3 or above, one single fault can be overridden and you can still operate safely. Just to make that a bit clearer, if you look at just a very simple analysis of 2 pressure switches, and if we had 2 pressure switches in a 1 out of 2 voting configuration, we can, if you might, the typical expected failure rate for a switch be around about 1 in 20 years, 1 in 20 to 1 in 50 years. So the probability of having 2 failing at the same time is actually quite low, looking at this middle column here. But the problem is, having 2 of them, we've actually doubled our spurious nuisance trip rate from 1 in 25 years to basically 1 in 12 years, because we've got twice as many of them, we'll fail twice as often. So if we're doing a 1 out of 2 vote on that basis, we've actually got a good safety outcome, but we've got a pretty poor process availability outcome. Remember, we've got, say, 10 pairs of these 1 out of 2 voting pressure switches. We'll have, on average, 1 failure every year. If we've got 10 pairs of them, each one going to fail 1 in 12 years. So 10 must fail 10 times in 12 years, or more or less 1 in 12 years. So we went 2 out of 2. We fixed the nuisance strip problem, but we've now got our dangerous failure rate down to a level probably not going to be acceptable. So we're going for a 2 out of 3 vote. We've actually been able to achieve a satisfactory dangerous failure frequency and quite a good spurious strip frequency. Difference between 200 years and 600 years, it sounds like a lot at 300. It's a 3-to-1 ratio, but the most important thing is that this number, 200 like 600, is much greater than the typical other reasons that are going to bring a plant down. You'll have an earthquake, perhaps, or a loss of supply, power supply, loss of feed availability, more often than 1 in 200 years. It's usually probably going to, that'll happen once every 20, once every 40 years. So provided the nuisance strip rate is significantly lower than that, with a bigger number here and here, it's okay. But this number here would become a real burden on the plant. So a 2 out of 3 voting architecture, one of the manufacturers, one I work for, Triconics, has an architecture like this, and I'll just quickly step through it. It has 3 processes, and then importantly the I/O is also triplicated, so the inputs are read 3 times for each point in the field, and the outputs are also handled by 3 separate outputs, and then there's a hardware voting circuit for every point. So this is a bit of a detailed look at the way the input module is working. We might have 32 or 64 points on our input module, but each point is being read by 3 separate circuits, and its result is being passed across to an I/O bus to a main processor. It's happening here, it's happening here. There's things like dangerous failure modes which could exist, such as a short-circuited opto-isolator. It could be normally, remember, these safety systems don't expect to experience changes in their input very often, so we'll have maybe a pressure switch hooked up to this input. All things being well, that pressure switch is going to stay there for 4 years or 8 years in the closed contact condition. How do we know we're ever going to be able to see an open contact in the field? If we get an open contact in the field, we'll have no volts here and we'll have a 0 here, but we've normally got a 1, obviously, because this is normally a closed contact, giving us a volts here and a 1 here. What this little bit of diagnostic circuitry does is we have a self-checking function where the input is actually short-circuited, pulled down by the voltage on this, at this point is pulled down to 0 by this solid-state relay here, which forces the opto-isolator to read a 0 output. If we don't get a 0 output read, we will know we've got a fault either in the multiplexer or in the opto-isolator. So that's a typical self-diagnostic circuit. You'll find that on most safety PLCs. I'd say all safety PLCs should have something like that. So this is not proprietary to Triconics or anything, this idea. It's just a good basic building block, and one of the things that distinguishes a safety PLC from a regular PLC. So by doing that sort of diagnostics, this is how we get the ability to continue to run and when we get a discrepancy between the 3 legs. So that previous slide was about a digital input, but for analog inputs, we expect to see 3 readings in very much the same range. If we've got a 3 input analog, 3 TMR analog input, because there's some noise on the signal, we expect them to be reading slightly differently from each other. Every time they're read, we normally expect the red and the green and the blue to be randomly one higher than the other, or taking it in turns, or not quite turns, but randomly. But if they'll expect it to be the same within a certain error band, but if one value goes off, perhaps up past the trip point, then having the other 2 in more or less agreement with each other will allow us to keep running and achieve a high reliability on the plant. With digital outputs, same type of thing. We have a fault-tolerant voting circuit. Remember I said there's a fault-tolerant voting circuit. Oh, sorry, there's a voting circuit on the output of every point. So this part of the circuit represents the common circuitry for 32 points, and this part of the circuitry is now for every individual point. We've got a circuit consisting of 4 switches. The purists amongst you might think we should have 6 switches here, so we can have A in series with B, and B in series with C, and C in series with A. But if you look closely at this switch here, it's actually driven by the result of A and B. So this becomes basically the Boolean equivalent of a circuit with 6 switches. It just has 2 less switches, so it's more economical and it takes up less space. Then it means in a given space we can use bigger sized transistors. These are solid state devices, they're field effect transistors usually, and the bigger they are, the more power they can, more current they can conduct. So it's good to maximize the size of them on your circuit board. So that voting circuit is in itself diagnosed. That would be a fault-tolerant circuit. If A goes, processor A, for example, gives bad and gives us a 0 output, we can maintain 1 output via B in series with C, because this one will be open, that one's open. And you can go through and see any other combination of single failure of the processors or switch itself. If this switch is stuck, we can override it. If it's stuck closed, we can open this switch, and this one, of course, which is not stuck, and bring our output to the de-energized state. We have all this loopback checking so that we can test these switches one at a time to see whether they can actually be opened. We open them for a millisecond, or if it's de-energized, normally de-energized output, we turn it on for a millisecond. Now remember, a 1 millisecond is not enough time for a load like a solenoid valve or even a large contactor to move. They take more like 20 milliseconds to actually change state. So 1 millisecond pulse is not going to matter. If it was a type of circuit that pulse would be seen, you can turn that what we call voter diagnostics off at a point level, so that that particular point is driving some electronic input which could respond to a 1 millisecond pulse. Turn it off and achieve that diagnostic function manually on a scheduled maintenance basis. It's obviously much better, and the way normally people do it is leave the automatic self-checking going on all the time. Same for analog outputs. We have a triplicated analog output circuit where each leg takes it in turn for 1 scan cycle at a time to drive the current out to the field, and we have loopback diagnostic to confirm that if the processors are trying to send a 12 milliamp output, that's compared to what's actually going out, and if it's not the right value or significantly different than what it should be, that diagnostic will recognize that and will turn that leg off, put a fault flag on the front of the module, telling the user that there's maintenance required, but meanwhile it'll continue to operate on the other 2 legs and basically for a long time. So one of the things to look for there in a system is no single point of failure. Having those diagnostics like we just went through, some examples of, and also being able to repair the logic solver online. If you can do those three things, you've got a reasonably good system, potentially. Bear in mind also, this no single point of failure, that's sometimes a misunderstood concept. The TUV approval for a safety PLC will talk about no single point of failure making the PLC unsafe. But if you think about the owner of the plant's point of view, he wants to know whether not only is the plant safe, but can it make product, can it make ammonium nitrate, can it make LNG? And if a single point of failure can cause a trip, that is a big economic penalty, and it has even greater impact if you look at it holistically. Think about the number of times a plant has accidents. It's most often, when you get down to it, happens during startup or shutdown. So having a reliable plant which doesn't trip spuriously is actually more safe than having a plant which does have a high rate of nuisance trips. And it's sad, but it's true that the TÜV approval process omits that consideration, because the TÜV can only look at the box in isolation. They're not doing it as a big picture analysis. They're just looking only at the safety of the device. And their reports are full of, and they quite acknowledge that, but it's up to the user to consider, has the system got adequate fault tolerance from a spurious trip point of view. So this is this data came from the Energy Safe Victoria, or what was then known as Office of Gas Safety. They put out this little guideline. This goes back to 1990, so it's 20 years old. But the classic information in it is true, that the 2 out of 3 voting architecture does achieve very high safety rating and low infrequent spurious trip rates. So distinct to the other types of architectures there. So we'll just, it wouldn't be fair not to talk about the other architectures. So this is a classic 2 out of 4 configuration, and the 2 out of 4 has 4 somethings. So it's got 4 processes here, and it's got 4 switches, so it definitely looks like 4 to me. But hang on a minute, over here on the left we've just got really 2 inputs. So, and if you look closely, there's 2 output circuits where this switch is being driven. This switch here is actually the diagnostic channel, and this one D is also the diagnostic channel. So in effect it's really a 2-channel system. The processors, certainly there's 4 of them, and they're doing some sort of comparison diagnostics. Just another way of drawing it, that's out of the TÜV report for that particular system. You'll see the this makes it a bit clearer, because the TÜV is it's trying to do their job. So they're correctly labelled here that the processors are really 2 pairs of 1 out of 2, and the outputs are actually 1 out of 2D, and the inputs are 1 out of 2D. D standing for high diagnostics. You can get this information from TÜV websites here. I won't go through it, of course, but it lists some specific restrictions that particular systems should follow. You can get access to this information from the either the TÜV website or from the vendor. It's best if it's available on the TÜV website. It'll tell you any restrictions that might occur or might apply to that system, because some of the systems get available in different configurations, and some of those configurations have more restrictions than others. So this is another architecture which is, this is looking even better, isn't it? So it's got actually 4 inputs and 4 processors here, and 4 outputs now, so that's looking good. Get to the fine print, we'd actually find that we've got 2 systems here, because it really only operates on 1 channel at a time. It'll switch over automatically between one and the other, so they're both getting exercised. But the most important thing is that this pair, it's either both running or none of it's running, and same for this pair. It's either all running or none of it's running. So in another way of thinking, it's actually just a 1 out of 2 system. So there's a fair bit of mythology, and you don't have to spend too long in this sector you'll hear people like myself coming up with all sorts of analysis and statements about the particular product. So I wanted to just try and dispel a few of the myths. I guess this is, from my experience, what are myths and what are facts. All this is subject to debate if you'd like to discuss it. Happy to do that. Well, one thing's for sure is the more electronics you have, the more failures you'll have. If you had 100 mobile phones, you'll have more failures than if you have one mobile phone. 100 cars, more failures than one car. So more electronics, more failures. The other thing is common mode failure. There's a lot of talk about common mode failure. I have to sort of skip across a lot of the details of some of these things, but I'm just sort of making you aware of the issues. The IEC standard talks about common mode failures, talks about not sharing common parts, services or support systems, not sharing operational maintenance procedures, and physical separation. And that's important because if the manufacturer is using a particular semiconductor microprocessor chip, say, in his DCS, and he happens to use the same microprocessor in his safety system logic solver, this is actually going contrary to this philosophy here, because you're getting to a point where you can have an unexpected and unwelcome, but definitely real event where the semiconductor manufacturer has to call the manufacturer of the safety system and say, look, gee, was really sorry, but we've got a batch of chips which was made, you know, and it's got this dangerous failure mode, we're really sorry. And the people who bought the logic solver from that manufacturer could well have the same failure mode occurring in both the DCS logic solver and in the safety system logic solver. So usually a very good idea to get a diversity of as much diversity as you can. Even if you're buying from the same manufacturer, go for one that has a different microprocessor and fundamentally different software set up in its safety system than in the DCS. The IEC 61511 standard, which reflects the requirements of the overall CIS, it also talks about common cause and what to do with it. And again, it emphasises here that the TUV approval is only looking at the safety PLC by itself. It doesn't look at whose DCS you're going to use that safety PLC with. So it's really up to the owner. That's the only person, owner or his advisor, to give them unbiased advice on what the overall combination of a particular BPCS and SIS is. And all too often we see that's overlooked. I guess everybody hopes that somebody is worrying about it, but maybe they think TUV is worried about it, but TUV specifically hasn't, because there's no way they can know whose DCS the system is going to be used with. All right, so another fact, definitely a fact, is that the impact of a failure depends on the architecture. In a 1 out of 2 system, failure is going to lead to a trip. In a 2 out of 3 or M out of N, it won't lead to a trip if it's a single failure. Another fact is that people can distort figures to produce high safe failure fraction. The safe failure fraction is a type of failure that is in the safe direction. So it's like a relay circuit going open circuit, that would usually be called a safe failure because we expect that's what's going to happen. There's a small number of relay failures which are stuck. You could have some sort of insect got into the side of the relay. If it's a large relay, be open to the air. And the insect will get in there, build a nest, so no longer can the armature move. So it's going to stay in the same condition, or the contacts will be welded shut because of an overcurrent situation. So if you go to any third-party data sort, you'll find that the safe failure fraction of relays is between like 0.7 and 0.95, say. Most of them are safe, yes, but there's a finite number which are unsafe. However, this little bit here is to do with no effect failures. So let's, for example, say, imagine the label falls off the relay. That's of no impact. It's neither safe nor dangerous. It's just a nuisance. Another thing would be a scratch on the surface of the housing. There's no impact. But if you start taking credit for no effect failures, it's really it's a distortion of the intent of the standard. So what happens is It allowed people, and this has been pulled up by the latest edition of the IEC 61508 standard, but it was allowing people to claim a higher fault tolerance, high safe failure fraction than what they actually had, and therefore allow them to use less redundancy than what they really should have used. It's definitely a fact that the high diagnostic coverage will tend to increase spurious trip frequency if all other things being equal, make it, the high diagnostics make it safe, but they also tend to increase the spurious trip frequency, especially in 1 out of 2 systems. The fact that a single channel logic solver might only just meet SIL2, SIL2 is kind of the bottom end of the scale, but there are some logic solvers out there which have certainly got a SIL2 approval, but when you take into account them being used in a real SIF with a real field device and a real sensor and a real output device, so a valve, it's most economical if the logic solver itself has a very low probability to fail to danger. Compared to the valve, it's most economical way to go is to assign, say, 10% of the failures to the safety PLC, 50% to the valve, and 35% to the transmitters. This is a guideline. So if the logic solver itself has a big contributor to SIL2, then you might have to go for extra output devices in series and extra sensors just to achieve even SIL2. So another myth that used to come out, I think it's hopefully been a bit beaten back, is that the TMR systems only depended on voting for safety. That was never true, but it was a good story. So I think you saw from the examples there that there's diagnostics, and when the TUV classifies the thing as 2 out of 3D, which is an objective independent assessment, then you can be pretty sure it is high diagnostics as well as 2 out of 3 voting. So the reason we know that's the case is because TUV allows the Trichronix TMR system to degrade 3210, which means you can have a fault, keep operating, have another fault, keep operating, and only when all 3 legs are bad does it fail to 0, just to stop the plant. Whereas either a 1 out of 2D or a 2 out of 4D, they will always fail this way. I haven't seen one that proves me wrong on this. I'll be open to suggestion, so please, if you have it, let me know. They'll fail 420 if it's quad, or 210 if it's dual. And the actual fact is, from what we discussed earlier, if it's 420 and 210, this failure, because we've got more electronics here, is going to happen more often than that failure. So in fact, what's going to happen is this will have more failures. The same outcome is the same as the dual systems. Actually, it's a bit perverse because the actual dual 1 out of 2D is probably better than 2 out of 4. Total loop fault tolerance. I'll start to wind up here because we want to leave a little bit of time for questions. It would be remiss of me not to talk about field devices after we talk about logic solver, but sometimes it's already some fault tolerance in the measurement. So on a lubricating oil system, we might have a low pressure switch and a low level switch and a low flow switch. That gives us some redundancy anyway, because one way or the other, low level in the reservoir tank is going to lead to a low flow and probably a low pressure anyway. So if we've got three switches for those 3 separate measurements, that's got some redundancy. What about output devices? We might even choose for the redundancy to ignore one. If we had a bad, if we had those 3 switches, we'd say let's just only vote 2 out of 3 on that and allow us one of these switches to be bad and keep operating our turbine. Output devices. This would be an example of a 2 out of 2 voting solenoid valve panel that was built. We had to build this for a client a long time ago now. It was back in the mid-90s or late 90s. 2 out of 2 voting, it depended on two valves being shut to, or two valves moving to trip the plant, which was designed to make it less susceptible to spurious trips. And obviously that made it more dependent on diagnostics. So we had these pressure switches, or these manual switches here, which when you push them would go into the logic solver and de-energize the output, and you'd see that output, the impact of that by the pressure drop on this gauge here. So when you did this button, you expect to see this pressure drop. In theory, that's a really good design if you're prepared to go and push the buttons. Although I guarantee you that the client never goes around pushing those buttons because they'll all be a bit scared to do it. A much better design, which would have been available, we would have used at the time, but is available now, was a 2 out of 3 voting solenoid valve, which has 3 valves, and one of the valves can fail either stuck open or stuck closed, and it's the way it's piped to achieve this 2 out of 3 voting. We have pressure switches to detect the status of the valve output. There's actually 4 pressure switches. You need 4 pressure switches to check the 3 valves. I haven't got time to go into the details of that, but it's true. And you, under control of the logic solve, you can de-energize the solenoid valves one at a time and check by the feedback from the pressure switches that all the valves are doing the right thing. And if one of them isn't doing the right thing, you can replace it online. So that's an example of a thing, and this is an example of where it's used on a big pipeline that's quite important for a lot of people in Victoria. These solenoid valves were a bad actor, as I call it, a contributor to a high spurious trip rate and potential interruptions to gas supply. The main valve itself is very robust with a very big spring, so if you vent the air off it, it'll close. But the replacing the single solenoid valve with this triple solenoid valve would greatly improve the reliability. I think at that point we might just take questions. Does anybody have any questions there?
Just anyone who has any questions, you can also just type them into the questions pane on your control panel. We've had one come through. Can you please give the link to the TUV website for further information?
Yes, for sure, absolutely. Yep. Oops. I just lost it. Getting to the end there. Yeah, if you'd like to make a note of that website there, there's two links. TUV-fs.com. This has all the manufacturers of safety PLCs, all their systems are all ones that have been approved by TUV, all listed there, and you can get access to the certificates and the test reports and safety manuals in most cases. So, and the other one below that, IceWeb, is an excellent resource. It has many white papers you can download and read from various organisations, and it's a very good way to increase your knowledge of this rather complex topic.
Thank you. So I've just got Mark Glickman. He's raising his hand, so I'll just unmute you, Mark.
Hello, what does SAS mean?
SIS?
What does SAS mean?
SIS stands for Safety Instrumented System.
Okay, thanks.
It's a good question because it's often the same, many words previously used for the same thing. So emergency emergency shutdown system, emergency trip system. Some companies had a particular name for them, critical instrument protective systems. But the generic name that was to replace all of those individual names is safety instrumented systems.
Okay, thank you. We might just leave it there. If anyone has any further questions, you can just shoot them through via email. I believe Jeff had his email up there earlier. So thank you to everyone who attended, and thank you, Jeff, for presenting.
My pleasure.